What's up, guys, and welcome to this walkthrough of question 6 of the 2017 final exam. This question is on gravitational fields and electric fields and is worth 18 marks. Okay, so let's get into the question. So a satellite of mass 700 kilograms is in orbit around a planet of that mass, 5.8 times 10 to the 24 kilograms, at a distance of 7.4 times 10 to the 6 meters. The planet is treated as a point mass. Okay, so the first question is a definition, which asks us to state Newton's law of universal gravitation. Okay, so the law goes that every particle in the universe attracts every other particle with a force that is directly proportional to their product and inversely proportional to the square of the distance between their centers. Okay, so from this definition we get the equation F is equal to G, the gravitational constant, m1 m2 over r squared. Okay, and we get 2 marks for the definition. For question 6.1.2, basically calculate the magnitude of the gravitational force F1 that the planet exerts on the satellite. So the force that the planet exerts on the satellite. Okay, and I'm going to go back to that same equation. F1 equals G m1 m2 over r squared. Okay, the gravitational constant has a value of 6.7 times 10 to the minus 11 times the first mass, which I will take as the mass of the satellite, times the mass of the planet, which was given in the question, times 10 to the 24, over the distance, which was 7.4 times 10 to the 6, and that entire value squared, and we get F1 is equal to 4,967.49 newtons, and we get 3 marks for that. Okay, so a second satellite of half the mass is in a different orbit at a distance 1.8 times the distance of the 700 kilogram satellite, and experiences a force F2. Calculate the ratio of F2 to F1. So 6.1.3, we want F2 over F1. Okay, so we can actually go and work it out. We can use the values mass 2, or the new mass, is equal to half of mass 1, and R2 is equal to half times the not half times, but rather 1.8. So R2 is equal to 1.8 times 7.4 times 10 to the 6. Okay, so we could do that and use that same equation that we used before, but a better way to do this question would be to actually use their relationships. Okay, so basically what we can say is that F2 is equal to Gm, let's say 1 m2 over r squared. I'm actually going to say that's m3 or m2 over r3 squared. Okay, and this time we have G, m3 is going to be half times m1. Okay, and m2 is just going to be the same, so this 2 refers to the planet. Okay, and then I'm going to use 1.8 times r, so r3 equals 1.2 times r squared. Okay, so that's just filling, so just instead of putting in the values, I'm just filling out the equation in ratios. Okay, then what I'm going to do is I'm going to get, if I plug that in, I get 0.5 over 1.8 squared times, I'm going to get G m1 m2 over r squared. Okay, and if we look at this, these two things are exactly the same, and this is F1. So what we can say, it's equal to 0.5 times 1.8 squared times F1. So if we want F1, or F2 rather, if we wanted F2 divided by F1, we just take 0.5 over 1.8 squared F1 over F1. These two cancel, and if we plug that into our calculator, we get a value of 0.15. So the ratio of F2 to F1 is equal to 0.15. And we get 3 marks for that. Cool stuff. Question 6.2. A small test charge of mass 20 grams, okay, I'm going to write that as 0.02 kilograms, and a charge of 1 nanocoulomb, which is times 10 to the minus 9 coulombs, is released from rest 0.6 meters from a charge Q in empty space. The test charge takes time 3.3 seconds to reach charge Q. Calculate the magnitude of the average acceleration experienced by the test charge. Okay, so an important thing to know is that for these charges, okay, so the equation for these charges we can say is F equals, from Coulomb's law, it's K, which is Coulomb's constant, Q1, let's say Q2, Q1, Q2, so one of these is the test charge over R squared. Okay, so let's actually change this to Q. As this upper Q gets closer, we also know that F is equal to MA. Okay, as this charge gets closer, the value of the force gets greater, and we can also say that from this we can derive that the acceleration is equal to Q over M squared, the R squared M. Okay, so as this Q gets closer to small q, what we have is the R gets smaller, and in this equation, if R goes down, then the acceleration must go up. So we don't have constant acceleration. So we must use our UVATs. Okay, so with that out the way, that's basically just understanding, so that we don't use speed equals distance over time or something like that. We must know that we don't have constant acceleration, or that our acceleration is changing. So we have to use UVATs. Okay, so we have UVATS. Okay, and our initial was from rest, so 0. Our final is unknown. The distance is was given as the acceleration is what we're looking for. The time is given as 3.3 seconds, and the distance was known as 0.6 meters. Okay, and then we can use the equation S is equal to UT plus a half AT squared. Okay, so U was 0, so this term goes to 0. So S equals a half AT squared. We know S was 0.6. Half acceleration is unknown, T is known. So the only unknown here is the acceleration, so we can solve for it. And A is equal to 0.11 meters per second squared. And that's the answer. That's the average acceleration. Okay, so that's 3 marks. Okay, question 6.2.2, calculate the magnitude of charge Q. Assume the acceleration we calculated. Okay, so basically, okay, so we're looking for the charge Q. How are we going to do this? Once you've calculated the acceleration, we can use this equation right here. So we can say that the mass of the test charge times the acceleration of the test charge is equal to Coulomb's constant Q small cubic Q over R squared. Okay, we know the mass was given as 0.02 kilograms. The acceleration we just calculated as 0.11 is equal to Coulomb's constant, which is 9.0. times 10 to the 9. Okay, so small q is 1 times 10 to the minus 9 because it's a nano. Big Q is the unknown, all over the distance of 0.6 squared. Okay, the only unknown here is big Q, so we can solve for Q, which comes out as 8,8 times 10 to the minus 5 coulombs. Okay, cool stuff, and we get 4 marks for that. Okay, so not too difficult and quite nice. Okay, then question 6.2.3. Why was it necessary in question 6.2.2 to specify the acceleration at 0.6 meters from the charge q? Briefly, okay, so we've already actually discussed this. So 6.2.3, we can say that acceleration is not constant. The electric field and therefore the force depends on the distance from the charge q. Okay, so basically this just explains, let's say, and hence force depends on the distance from the charge. Okay, so this is just explaining what I explained here, that our acceleration is dependent on the distance. As the distance gets closer, as we get closer, or rather it's moving this way, as this gets closer that way, r goes down, and so our acceleration goes up. Okay. Yeah, and that we get our 18 marks for. Yeah, nice, easy question. Yeah, so thanks for watching, guys, and I hope you found this useful.